I hope you're all well. Thanks for joining me on this review of an example on how to solve protein binding problems using a linear approach. So we're going to use the modified scattered plot, which is rearranging that Michaelis-Menten equation that described the relationship between what describes the bound concentration of drug to the unbound concentration of drug here. And this is the relationship. Bound concentration is equal to N, which is the number of protein binding sites available to bind. The free concentration times the free concentration all over the KD, which remember is the dissociation constant, or the affinity of the system. So the N is the capacity, the number of binding sites available. And KD is the concentration where half of the binding proteins are filled. So the lower the concentration where that occurs, the higher the affinity. So the lower the KD, the higher the affinity. And remember, KD is just the inverse of the affinity constant. Ka, or the affinity constant, is equal to 1 over Kd. So Kd is the inverse, or the dissociation constant. The lower the Kd, the higher the affinity. And in the denominator, we have plus the free concentration. And you'll notice if you're familiar, if you can remember your familiarity with the Michaelis-Menten equation, this is in the form of the Michaelis-Menten equation, right? N would be analogous to Vmax times concentration over Km, which is the concentration where you're at half of Vmax, plus concentration. So you see it's the same format. Now, if we rearrange this equation to get a linear form, which we have to do a little calculation. So we'd have to divide this side by free concentration. So bound concentration divided by free concentration, which would be our Y component, in our equation, is equal to, I guess you can do the math to rearrange this. This is going to be our Y-intercept, or our B, is N, or the number of binding sites available, times Ka, minus, this is going to be the slope. The slope will be Ka, and the X value is the bound concentration. So our X is going to be the bound concentration. Our Y is going to be bound concentration divided by free concentration. And our Y-intercept is the product of our number of binding sites times our affinity, Ka, and the slope of the line will be Ka. So we're going to put that in that form to be able to, we put all our X, Y components and plot those, and the slope of that line will be negative Ka. So the Ka is not going to be negative, but the slope will be negative. And the Y-intercept is going to be our number of binding sites available times our affinity constant. So if we know our slope and we know our Y-intercept, we can figure out both the N, the number of binding sites available, or the capacity of the system, and Ka, which is the affinity of the system. So what we're going to do then is take some data that has been given to you in this problem, and we're going to use Excel to solve the problem. Okay, so now I'm going to switch. I'm going to put all that data. Well, I'm going to put the D and the DP data in here, and I'm going to share this Excel with you, and we're going to work on this together. Okay, so we've been given free concentrations and relative bound concentrations at that same concentration. So here's our given free concentration and bound concentration. But remember, our Y value here is bound divided by free concentration. So what we have to do here is do some calculations, which is really easy in Excel. So we're going to say equals our bound concentration divided by, remember, divided by is a backslash, our free concentration. And then we just hit return, and that's our Y value. Now, one of the beauties of Excel is that we don't have to do this over and over again. As long as the relative same operation needs to happen, we can just take this. Notice how this goes from a bold, almost like a plus that's on the Swiss flag, to a plus sign that's not bolded. Once it gets there, it's right over this little square on the bottom right hand corner. You can take a left click and drag, and it'll do the same relative operation. So see, this one is B4 divided by A4. So this one's going to be B5 divided by A5. So as long as it's relative, it'll do that same, which is what we want it to do. So here's all our Y data. So now we have our given X data and our calculated Y data. So now we need to plot that data, don't we? So I'm going to insert a graph that's XY data, and I'm going to have it draw a line between these. And now I'm going to select my data. I'm going to add binding. I don't remember what I'm measuring here, so I'm going to just say binding for now. Okay, the X values are here, and our relative Y values are here, which we had to calculate. And yay, we have a line that it looks like a pretty straight line. We can't see where it crosses the y-intercept here, but we can determine it, can't we? So I'm going to say okay here, and maybe just as a reminder, we're going to add some titles, because otherwise I'm going to get confused. Our X data is bound concentration, isn't it? In millimoles per liter. And then our Y data is what we calculated, which is I should make these little concentration things. dP divided by D, and that's going to be a fraction, so there'll be no units on that one. And I'll go back and do that later. I think we can remember this. Okay, so now what we want to look at is, if you remember, we want to find the y-intercept, which in this case is n times Ka, isn't it? So our y-intercept. So we're going to say, how do we get the y-intercept of this line? We're going to say intercept, if you remember. You can look that up again if you've forgotten what it is. Intercept. Okay, and then we have to put in our data, don't we? And it says known y's here, so we're going to put in our known y's, which are here. And then comma, our known x's, which are right here. So our y-intercept is wait a minute, I did that right. Let me check it again. Known y's and our known x's. And then our slope, which is our minus our Ka, is going to be, we figure that out by saying slope, and then our known y's and our known x's. And again, that's negative, so our Ka in this case is going to be, you can either say the absolute value, absolute value, or you can just put a negative on there, whatever makes you happy. Okay, and now, so how are we going to figure out our n from here? N is going to be equal to this divided by Ka, right? Which is right here, which is B13. So our N is 1. So our number of sites available is 2. And our Ka is 856. All right, I'm going to stop there and I'll come at you with another second part to this. Thank you.